Hello everyone. In this video, I'm just going to work through this worksheet. This will be assigned for you to do in class or as an assignment for class. And if you needed some backup, you can watch this video and maybe it'll help to see me work through some of these. All right. So in this worksheet, we're comparing one compound against another one to see which one would have the greater polarity, or what kind of polarity would we see. And judging from the polarity, we would identify the intermolecular force that compound would experience. So for each of the following pairs of molecules, identify the IMFs and determine which is most polar and explain your reasoning. All right, so here we go. For each one of these, we'll need to first draw out the Lewis dot structure. You've got to know the Lewis dot structure in order to really determine polarity. For these two compounds, I drew out the Lewis dot structure. This would be the Lewis dot structure for carbon disulfide. It would be linear, and it would definitely be nonpolar. Sulfur difluoride. If you drew out the Lewis dot structure, you would have these two lone pairs, which creates a bent structure. It's totally polar. On this side of the molecule, we're going to see a partial negative charge and a partial positive charge at the top, because electrons are going to be pulled toward the fluorine. So one side of the molecule is going to be negative. This would be the negative side of that molecule. So it's definitely polar, so it's going to have a dipole-dipole IMF. All right, for the next couple, I drew out the Lewis dot structure. We've got nitrogen trichloride, and we've got oxygen dichloride. All right, now if you drew out the Lewis dot structures, you're going to have a trigonal pyramidal structure here. You have a bent structure here. They are both polar, but this molecule is going to have higher polarity. The reason that this has got higher polarity, it really has to do with the bond angle. All right, this has got a lesser bond angle than the angles here between these chlorines. I think that this comparison is probably a little bit beyond where we're at right now in honors chemistry, but I will just say that because this is a steeper angle, it's going to be more polar. Why don't we just leave it at that? And let's just move on. All right, for this next comparison, boron trihydride and ammonia. You might remember that boron is an exception to the octet rule. We're going to have a trigonal planar structure here, and with ammonia, we've got a trigonal pyramidal structure because of this lone pair. That's going to leave us with very different molecules. We've got a nonpolar boron trihydride, where we've got a very polar, actually, ammonia. In fact, it's going to exhibit hydrogen bonding. With this next comparison, we've got chlorine, which is nonpolar. It's going to exhibit London dispersion forces for its IMF. Phosphorus trichloride, we've got this lone pair of electrons, so it's going to be a trigonal pyramidal structure. It's polar because electrons will be pulled toward the chlorine, and so that gives it a negative side. And we're going to see dipole-dipole interactions. For this next one, silicon dioxide and carbon dioxide. I really don't like this example. The reason I don't like it is because silicon dioxide and carbon dioxide don't have similar structures in reality. You might be tempted to write silicon dioxide as I've written it here and then compare it to carbon dioxide, and they have very similar structures, but in reality, silicon dioxide doesn't look like this. You know, silicon dioxide is actually sand, okay, and glass. Glass is also silicon dioxide. Obviously, these are solids at room temperature, where carbon dioxide is a gas at room temperature. Why would they have such entirely different properties if that was true? Well, in fact, it's not true. This is not a valid structure for silicon dioxide. I'm going to draw it for you right now, and then we'll come back to this. Here's the beginning of what I wanted to write here. So here would be silicon dioxide. But in reality, what we have is what we call a network solid, okay? And you could not possibly have known that from what we've been covering in class. So, I mean, I don't like this question. I feel like it was kind of a trick question. So really, this is known as a network solid. You can kind of see what I mean by network. You know, it's like these covalent bonds are really binding all of these atoms together as kind of in a network, right? Where this is just a lone molecule floating around as a gas. So they're very different situations. Let's move on. All right, methane and this is called dichloromethane. You can see how they're very similar molecules. What we've done with methane here is we've added chlorines or substituted chlorines for these hydrogens, and I put the chlorines there. So there's a central carbon there. This looks very much like methane, only it's got chlorines on one side of it. These are both tetrahedral structures, and just as a side note, it wouldn't matter where you put the chlorines around here. You would always have this exact same structure. And if you had a 3D model in front of you, you would be able to see that very clearly. It wouldn't matter where you put these things around this molecule. You always have the same molecular structure. Anyway, this is going to be polar because we've got a negative side. Those chlorines are going to pull electrons strongly to one side of that molecule. All right, you got a dipole versus an LDF. All right, I just drew the structures here for silicon tetrabromide, and this is called cyanide. So cyanide is going to be a dipole. We're going to have electrons being pulled toward the nitrogen side here. So we're going to have a negative side and a positive side. This is going to be nonpolar. So we're going to have LDF. And this will have a dipole. I'm not going to bother writing that. That's polar. It's got a dipole interaction. All right, nitrogen trifluoride versus phosphorus trifluoride. Okay, so here's another one. This is an interesting one. Really pay attention here. All right, both of these molecules are structurally the same kind of. You know, this is a trigonal pyramidal and a trigonal pyramidal. So which of these is more polar? They are both polar, but phosphorus trifluoride is going to be more polar. Here's why. Okay? There's a much bigger difference in electronegativity between phosphorus and fluorine than there is between nitrogen and fluorine. Okay? So in other words, in phosphorus trifluoride, there's going to be a greater pull of electrons toward fluorine and toward fluorine and toward fluorine. Here, the pull of electrons toward fluorine is less because nitrogen also has a pretty high electronegativity. Okay? So electrons are not as strongly pulled toward fluorine in this molecule. All right, so what does that mean? It means that this molecule is going to have a very negative side to it here. Electrons are being pulled toward fluorine very strongly here. This side of the molecule is going to be very negative versus the negativity of this side of this molecule. I hope that makes sense. Okay, so in other words, this is going to be more polar, phosphorus trifluoride, more polar. They're both going to exhibit dipole-dipole interactions, but this would be more polar, therefore this would have higher melting points, higher boiling points, and so on.